This video is the solution to the exam 2 review problems, problem number 4. Alright, so let's just jump right in. There's lots of parts to this problem. The first part, we're looking at steady state error, so we're looking at E here in the block diagram, for the case where the reference signal is a unit step. Now, this block diagram has it set up where there could be an external disturbance, but for this part we're assuming the disturbance is set to 0. Alright, so we've done this before, and so the question you should start asking yourself, if the reference signal is a unit step, what is the type of the system? So I look here and I look at the transfer function, identifying the parts that we've always done. Here's D, here's G, and I know that if there's a pole at the origin, this makes this a type 1 system. And so from there I can say for part A that the steady state error for this system is 0, because that's a unit step and it's a type 1 system. All right, but for part B we have a little more work to do, because in part B we're looking at the steady state error for the case where the reference is a unit ramp. Okay, so a type 1 system has a finite non-zero error for a unit ramp input. All right, so the way we tackle that is we know the form of the error transfer function. Okay, so I'm going to call this E over R. That's the error transfer function, and the form of that is 1 over 1 plus, in this case, D times G. All right, and so we can identify D. We know D is K times S plus 1 over S. And we can look back up here and we can see G is 3 over S plus 2. So we have these two things that we can plug into the error transfer function. Okay. From there, what we're looking for is the steady state error. So that's the limit as t gets really large of the error signal. And I can use the final value theorem to get that. That's the limit as s goes to 0 of s times E over R, the transfer function, multiplied by R. Okay, so plugging everything in, we have limit as s goes to 0 of s, and then R for a ramp is 1 over s squared. This is a unit ramp, so we have 1 over s squared. And then we just write down the transfer function, which we've already determined to be this. Okay, so the transfer function is 1 over 1 plus D K S plus 1 over S times G, 3 over S plus 2. Okay, so we notice that one of these S's here cancels, and so now I have an S in the denominator. So this would be S times 1 plus KS plus 1 over S times 3 over S plus 2. And if we distribute this S through, we will get limit as S goes to 0 of 1 over S plus, and now this S cancels with this S, and so we would have a KS plus 1 times 3 over S plus 2. So at this point, we can plug in S equals 0, and everything's going to work out because we can easily find that limit. All right, so in this situation, we have 1 over, and then this particular S is 0, and then we'd have a K times S 0 plus 1 times a 3 over 0 plus 2. Okay, so it looks like our answer is 1 over 3k, and then this 2 in the bottom would show up in the top. And so that is our steady state error, 2 over 3 times k. So sometimes I would ask, what happens to the steady state error as you increase the gain of the system? So as k increases, the steady state error would decrease because k shows up in the denominator. All right, now we're looking at part C. And in part C, we're looking at the steady state output, assuming that the reference signal is set to 0, and now we have the influence of an external disturbance force. We're going to model that with 0.2 times u of t. Okay? So again, the reference signal is set to 0, and we're looking at the steady state output. So we still just apply Laplace transform theory to answer this question. So with w of t equals 0.2 u of t, we know that cap w, the Laplace transform, would be 0.2 over s. We also know the Laplace, or the transfer function between y and w. All right, so y over w, we derived this in class. That would be, all right, we have to identify these parts again. Here's g, here's d. Y over w is g over 1 plus dg. All right, so to get y of infinity, which is the limit as t goes to infinity of y of t, we can use the final value theorem. And so we take the transfer function y over w and we multiply by w. All right, so plugging everything in, here's y over w, and we know that w is 0.2 over s. We get limit as s goes to 0 of s times y over w, so that'd be g over 1 plus dg times 0.2 over s. And so we notice that the s's here cancel. And so at this point we're taking limit as s goes to 0, and we can plug in to these expressions. All right, so we know g is 3 over s plus 2, and we know that d is k s plus 1 over s, and then we have another g, and we're letting s go to 0. We still have this 0.2 out here. Okay? And so what I get when I plug to 0, I can look at this and make a logical conclusion without doing any more algebra. Because on the top, when s goes to 0, we're looking at here, we get 3 halves times 0.2. That's a finite number on the top. On the bottom, we have 1. All right? And then we have a pole at the origin. So as s goes to 0, this whole term in here, when this s equals 0, this one right here goes to, when that's 0, we just get 3 halves. So this particular term, as s goes to 0, this is heading to infinity. So we have 1 over infinity, which in the limit is 0. So in the long run, this external disturbance, the compensator, that 0 at the origin, pole at the origin, ended up having the effect